All right, we are talking about graphs, graph theory, right? More about graph theory. This time we're going to get down to some technical details. Last time I was just trying to convince you that graph theory is important in many different contexts. I hope that you are well convinced. Even if not, we're going to do it anyway. So today, some more technical details about graphs. I wanted to start actually from a very basic consideration, which is just what is a graph? What is the definition of a graph? What is a graph? Really? What really is a graph? What I mean by that is something like, for example, I said last time, my sort of definition, I suppose, of a graph is I just said, well, it's like a thing that looks like this, or something like this. It's got a bunch of dots and lines, right? The dots are called vertices, the lines are the edges, and this is a graph. It's a thing like that, made up of vertices and edges, all right? But this is not really a great definition of a graph, just because I can say, like, that picture that I drew, that's a graph. How about this? What if I made it so that the edge on the bottom, like, is curvy instead of straight? Are those the same graph, or are they two different graphs? Now, if you believe that the graph really is a picture, then you would say those are two different graphs because they're two different pictures, right? The one on the right has a curvy line on the bottom, whereas the one on the left has a straight line on the bottom. But actually, this is not an important distinction between these two graphs, right? These two graphs, they look slightly different, but mathematically speaking, we consider them to be the same graph. They look slightly different, but we consider them to be the same. Because all we care about with a graph are the vertices and their connections with one another. We don't actually care precisely how you draw one connection or the other. Precisely how you draw them is not important. What is important is what are the vertices and what are the connections. Let me just say that graph is also the same as, how about this? What if I do those 5 points, but I connect them all sort of in a circle? There's still 5 points that are connected in that way. And then maybe I'll make that other one come on the inside rather than on the outside. This, too, is considered to be the same graph as those other graphs, all right? It looks different. This one looks quite a bit more different on the page, but it is mathematically considered to be the same graph because it has the same points and the same connections. Now, precisely where I drew the points and where I drew the edges is different, but this is the same graph again as these two up here. This point out, I drew it as if it were outside. Here I drew it as if we're inside. It doesn't matter though, because in either case it's just a single point that's connected to this other point. All right, this also is the same graph. Now, when I say all these things, this should make you really wonder, in this case, if these are all the same graph, then what is a graph really? If it's not the picture, what I'm trying to tell you is you can draw the picture in many different ways, but they all represent the same graph. So what is the true nature of the graph if not the picture? It is just the vertices and the edges. So here's a real definition of a graph. This is one of those times where the mathematical definition is actually quite far removed from the way that you typically think of the graph. You think of the graph as a picture, but the true definition is not using pictures at all. So this is the true definition of a graph. It is a graph consists of a set of vertices. A set is actually kind of the Sets are kind of the basis of all of mathematics. These days, in the 20th century, sets became the foundational language that all of mathematics now is expressed in terms of sets. Sets of numbers, sets of geometric shapes, and things like that. So the true definition of a graph is a set of vertices with a set of edges, and those edges are described by pairs of vertices. All right. This looks very technical, but I mean it's not really complicated or difficult to understand, but it looks kind of crazy when you write it all out. So for example, that same graph that I had before, I'm going to give names to all the vertices just so that we can refer to them in our listing of sets. So I'm going to call them, let's say A, B, C, D, E, and F, like that. All right. So what is this graph truly? It is not the picture. The picture is a representation of the graph, but the true nature of the graph is just as a bunch of sets. It's a set of vertices. So I'm going to say this graph is, what is it? It has vertices given by a set. And a set, mathematically, you always write it with these curly brackets. So the set of vertices is A, B, C, D, E, F. And the set of edges is this. Remember, I said is a set of edges which is described by pairs of vertices. And so the way I'm going to write this is just as pairs of vertices. So AB, that means there is an edge from A to B. And then I also have BC. I also have CD, DE. I'm just writing down a list of all the edges that I can see on the graph. There's also an edge A to E. Doesn't matter what order you write these things in, as long as you get them all. And there's also an edge from E to F. So that's what the graph is, all right? The picture is a representation of the graph, and when you are thinking about the graph, you should think of it in terms of the picture. But the picture is not its true nature, because like I said, there are many different pictures you could draw to represent this graph. The true nature of the graph is just all of this stuff, all right? So technically, if you want to be super technical, we say this graph is a pair of sets, right? The first is the set of vertices, followed by the set of edges. So if you really want to write this in full technicality, it would be this. A, B, C, D, E, F. That's the set of vertices. This is the set of vertices, followed by the set of edges. A, B. I'm just writing this set again. And if you want to do this correctly, you better have all the brackets in there. Like that, all right? That's the set of vertices, and then this over here is the set of edges. And those two things together define the graph. All right? I said before, I hope you agree, this is kind of like super technical, because when you write it this way, it just looks like a whole bunch of nonsense. But this actually represents that picture up there. All right? This is the true nature of the graph. It is a bunch of sets, a pair of sets. And this is actually what those two homework questions are about. All right? That's what the graph is. So you can go from a picture, like if I show you a picture, you can turn it into this kind of representation of the graph. This I would refer to as the formal representation of the graph. It is all of this stuff. If I show you the picture of a graph, you can write down the formal representation. Or if I show you something like this, you can draw the picture of a graph. Let's try and do one like that. So this is a very simple example. This is like what those homework problems are about. How about draw this graph? And I will describe to you the graph in its formal description is the set A, B, C, D, followed by the set AC, BC, AD, CC, BD. Like that, all right? That is a graph. All of that stuff that I wrote there, that is a graph, and your job is to draw a picture of it. This is not really difficult, although just looking at the letters without starting to draw anything, I really have no idea what this graph looks like, the picture of it. But I mean, it has 4 vertices, right? So I would just start by drawing those 4 vertices, A, B, C, D. I suppose it doesn't matter what order you put them in. I'll do them like that. And then start drawing the edges that you see in the list of edges. So I see AC, all right, that's an edge there. BC, that's an edge there. AD is an edge like that. CC, I guess that's an edge from C back to itself, all right, like that. And then BD is like that, all right. So that's what the graph looks like. This is a picture of the graph. All right, so this is just very simple, going back and forth from a picture to the formal description of a graph. All right, anybody got questions about that? Your answer will look different depending on the ordering in which you drew those vertices. Like actually this is the same as if I had done the vertices, say, like, I don't know why I would have done this, but if I had done them like A, D, B, C like this, then the graph would look like that. And those are the same graph. They look kind of different, but they're not different. They have 4 vertices which are connected in certain ways. They are the same graph. All right. Anybody got any thoughts about that? This is I hope you feel like this is very simple, but necessary to talk about in terms of the definition of what a graph is. All right. It's very hard to look at this and tell basic properties of the graph. Like looking at this list, you really can't tell if it's connected or not, or what the degrees of the vertices are. You have to draw the picture to get that kind of insight. All right, I want to talk about something specific. So what we're going to talk about today is our first kind of big topic in terms of graph theory, is called Euler circuits. This is our first big topic in graph theory. Euler circuits. This is actually based on the original graph theory problem that was first studied by this guy named Euler. Can I just say, this is pronounced like that. Euler. It's a German name. Don't say Euler. If you say Euler, I will immediately correct you and say Euler. And you will remember, oh yeah, he said Euler in class. I'm going to say Euler like 100 times. So please say Euler, not Euler. This may be a little confusing. You may have heard of another famous mathematician. Anyone know that guy? Euclid, not Euclid. You got to keep it straight. Euclid is Greek, pronounced Euclid. Euler is German, pronounced Euler. Anyway. Euler circuits. Euler is one of the greats of like sort of 1700s European mathematicians. Euler is probably the top of the list of European mathematicians of all time. Euler did a lot of very basic stuff in calculus, but he also did tons of other stuff. And Euler is kind of the originator of graph theory, at least as far as the history of graph theory, if you trace it back from today to when it kind of began. It sort of began with this one, actually, I'm going to call this the original graph theory problem. There's this one math problem which is regarded as the beginning of graph theory. It's called the 7 bridges of Königsberg. This was a city. This was a math problem. Euler lived in this city, and the idea is this is kind of a true story, I guess. The city of Königsberg has a river that goes through it, and the river has 2 islands in it. All right, so this is all the water, all right, and those are 2 islands in the river, and those islands are connected by bridges to, this is like right through the middle of the city, and so there are bridges from the islands to the land, and also there's a bridge in between them. So the bridges go like this. One goes here. What? Sorry. One goes here. There's one bridge here and one bridge here. And then on the left side, there are bridges, 2 bridges like that and 2 bridges like that. All right. This is a real sort of place that really exists. Although today, I think not all the bridges are still there in the modern city. But anyway, those are the 7 bridges. All right. And there was a sort of popular local math problem involving these 7 bridges, and it was just this this question: can you walk across all 7 bridges without repeating any? And ending where you started. This is the question. All right. Can you walk across all 7 bridges without repeating any and ending where you started? And you can, anybody can sort of try to think about this. Like, let's say I'm going to start in this, the island on the right side. Can I actually cross over all 7 of the bridges? Maybe I'll try and draw this with a red line. Maybe I'll go up here first, over here, down. What? Sorry, I didn't want that. Maybe I'll go up, over, down, down, back up. Actually, I'm kind of, no, I'm not stuck, am I? I kind of am. I can go back up here, but now I'm stuck at the top and I can't get back to either of the 2 islands. So that sort of suggestion that I just did is not a valid solution to this question. You want to cross every bridge without repeating any and end up back where you started. This way apparently is not going to do it. Maybe I should have, instead of coming back up at that point, I should have gone back across here. Now I've kind of finished too early. I could go back over there. Then I'm going to get stuck again anyway. All right? The answer to this question is no, it is not possible. But the real issue is trying to demonstrate in a simple way why is it impossible. So I'm just going to say, this is not really a spoiler here. The answer is it's impossible. But as a math problem, the problem then becomes like, how can you actually logically demonstrate that it really is impossible? How do we think of this mathematically? What is the appropriate way to look at this? Like, what kind of a math problem is this really? Well, on the surface, I would say this looks like a geometry problem because it involves, a shape of some sort, and you're doing some stuff with the shape, right? But all of the classical tools of geometry, like distances and angles and things like that, actually this problem has nothing to do with distances or angles. So you can't use any of the geometry that you likely learned in high school is just irrelevant in a problem like this, all right? Because actually, I just drew this diagram with these bridges, but, the specific geometry of this bridge is totally unimportant. All that matters is that there is a bridge connecting this island to the top, and then there's 2 bridges connecting this one to this side, right? But none of the specific distances or angles or anything, none of that matters. Okay, so I'm going to say, how do we think of this mathematically? I would say it looks like geometry, but it's not actually. Really, it's not. All right, and this was Euler's big realization that it is not appropriate to think of this like a geometry problem. Instead, it is appropriate to think of it like a graph theory problem, which never existed before that, but that's how you really should think about this. It looks like a geometry, but really it's not. It's a graph, all right? So Euler's big idea was to basically invent graph theory in order to solve this problem. But Euler's big idea was what we're looking at here. Sorry, I keep on scrolling. Basically, we have the two islands, and it doesn't matter what shape the islands are or anything like that. All that matters is like this is a thing over here. So I'm going to make a sort of put a big dot here, a big dot over here. Those are just like two things. And then there's also the land up at the top. Again, it doesn't matter what the shape of any of this stuff is. It's just that there is like an area at the top, and there's also an area at the bottom. All right? Now, it's true you can walk back and forth along the top, but that has nothing to do with anything because all you care about in this problem are the bridges, right? So the top, you might as well just consider the top to be all one thing by itself. And then we have these particular connections. There's one there, there's two there, there's two there, there's one there, and there's one there. All right? So Euler looks at this instead and just like forget about all the geometric information that exists in the picture. All you care about are those 4 points and those connections. So when I say it's a graph, it's this graph in particular. Come on. It's a graph of 4 vertices. The two in the middle represent the two islands and a bunch of edges which just represent all the bridges. There's 2 bridges like that, there's 2 like that, and there's 1 like that. All right? So these vertices, you could say this one is like the island on the right. If you want, this is the island on the left. And then the vertex on top represents the top bank of the river. And the vertex on the bottom represents the bottom bank. All right? Like I said, geometrically speaking, this is not really accurate at all because the islands are much smaller than the banks on the top and the bottom. But none of that is important for this bridges problem. All you care about are the 4 different locations you can end up and all the bridges that connect them. Okay? And now that we've turned it into this graph, the question now becomes, can we find a path through here? Really, I said we want a path where you start and end at the same point. And so really that's called a circuit. This is one of the vocabulary words from last time. I hope you remember. A circuit is just a path through the graph which starts and ends at the same point. Can we find a circuit which... The important thing in this graph would be a circuit which uses every edge once, right, and doesn't repeat any. That's the whole bridges problem is about, can you walk across every bridge once without repeating any? So can we find a circuit which uses every edge once? No repetitions. All right. And that is called an Euler circuit. That's what I said we were going to talk about. It's named after Euler, sort of because he came up with this whole thing. So this is called an Euler circuit. I'll just write that as a definition. A circuit using each edge exactly once. Exactly meaning it doesn't use it more than once and it doesn't use it less than once, right? Every edge gets used exactly once. Is called an Euler circuit, not Euler. All right, that's an Euler circuit. And this question actually, so Euler, I'll just tell you, Euler figured out how to decide, and actually Euler came up with a very simple method by which you can figure out if any graph that I draw has an Euler circuit or not. This is actually, once you know how to do it, it's a very easy problem. Say on our next homework or something, I show you a graph and you tell me, does it have an Euler circuit or not? That's really easy to do if you know what you're looking for. All right? This is called an Euler circuit. And this comes up actually in important settings. I would say Euler's problem about walking across the bridges is not really important for anything, but there are many real-world scenarios in which you would want to make an Euler circuit. For example, I got an example here where Euler circuits might come in handy. How about I'm imagining a grid of streets like this, maybe? So thinking of this as a graph with vertices at each little intersection like that. And let's say you got the snowplow guy. Let's say Mr. Plow lives there. This is a Simpsons reference. Mr. Plow lives here, and let's say when it snows, Mr. Plow wants to plow all the streets in his neighborhood. And the best way to do this, of course, is if you didn't have to repeat any street. So let's imagine Mr. Plow's, this is not very realistic, but let's say Mr. Plow's plow is so big that it can just go straight down the middle of the street, and that's good enough. One pass down each street. The question is, can Mr. Plow drive every street once and end up back at home? At Ham. With no repeats. No repeated streets, right? This is the question. This is another Euler circuit problem, although this one you can imagine someone in the real world might actually want to know the answer to this. You could even ask more sophisticated questions. Would be like, here's a little follow-up. If not, how many repeats are necessary? We're going to talk about all these questions. And if you know what you're doing, actually these questions are not terribly difficult to answer. Like I happen to know in this example, and I'm just making this up right now, but once you know what to look for, it's easy enough to answer these questions. In this example, actually, Mr. Plow would have to repeat at least 4 of those streets. It's a true fact. You cannot drive all of these streets without any repeats. And in fact, if you really wanted to do it, you would have to do kind of a lot of repeats. You'd have to repeat at least 4 streets in this particular arrangement of the streets. All right. So all of these questions here can be answered if you know some basic graph theory about Euler circuits, and that's what we're gonna be talking about. All right. Any thoughts about this? Let's look at an example where it's not so hard to answer the question. Like all of these examples, I'm just kind of telling you the answer, and I'm saying eventually we will learn how to do this. But here's an example which is not so difficult. How about this graph here? This one has a vertex in the middle there, and it has some edges on the sides. All right. How about this graph? Does this one have an Euler circuit? Actually, this one does have an Euler circuit. So I'm going to see if we can draw an Euler circuit or specify an Euler circuit. So this one has an Euler circuit. I hope you don't mind. I'll just write E-circ, Euler circuit. This one does have an Euler circuit. That means you start in one point, you drive around and you use every edge once, and you end up back where you started. Can I try to say what that is? I'm just going to write like a big list of vertices. Let's imagine we're going to start at A. Anybody think you can do this? Anyone want to try to shout it out? What if we start at A? Can someone tell me where should I go from A? Take a moment. See if you can figure out a decent route here. And then someone want to shout it out? There are actually several ways you could make this work. Anybody feeling it? Anybody waiting for somebody else to feel it? You feeling it?
I just figured out, I think I may have lost it. I think I have A to D first.
Okay. I'll try and draw a little.
And then D to C.
All right.
And then C to, oh, no, I lost it.
Okay. Anyone else want to try? I feel like this is pretty good so far.
You can do, after that,
Yeah.
D, C to A.
Okay.
And then use the other ones, do A to D again.
All right.
And then D to E.
Okay.
E to C.
All right.
C to B.
Okay.
B to E. E to B.
Mm-hmm.
And then B to A.
All right. I like that. That looks pretty good to me. It hits every edge, and it didn't miss any edges, right? And it didn't reuse any edges. This is an Euler circuit. So if I were to write this out, I will try to follow the line that I drew on there. I want A to D, and then to C, then to A, then to D, to E, to C, B, E, B, A. I think that is what I drew with the red line. All right? Can I just go over a few little artistic do's and don'ts? This is not an art class, but you are going to be drawing diagrams like this in the homework from time to time and on your tests and something. Please keep in mind that your audience when drawing this picture is me, and I need to be able to understand what your picture means. Now, I don't know if any of you felt like I was drawing this in a somewhat sloppy way. When I drew this line, you will notice that my red line does not go through the vertices, and it also doesn't follow right on the edges. I always drew the line kind of next to the edges. This is not because I'm a sloppy gentleman. This is because actually, if you follow the lines exactly, it will not make any sense when you're done drawing it. So I will say, when you're drawing this, this is not a mathematical comment. This is just about the drawing. Follow next to the edges and vertices. Because if you don't, can I just say, don't do something like this. Here's what it looks like if you don't do that. I'm drawing the same picture again. Some people, I see this on the homework all the time. They're like, oh, can I just like put the arrows, right? Go down here, then back up here, then back over here, across. Oh, that's not the way. Down here, over here, up there, up there, up there, up there, right? Isn't that just as good? The answer is no, it's not just as good, because I can't tell anything here, right? When I look at this, now you know that you started here and then went down this one, but also maybe it looks like maybe you went down this one, and then from here, which way did I go? Up there or across there? You can't tell. So I'm just saying this picture here is not good enough to show me that you know what you're talking about. All right, this is much better. It might look a little messier or something, but that's the way it's got to be. All right. Make sure you draw a nice curve so that I can see where it goes from one point to another. Of course, this is kind of the gold standard, right? If you actually write out the letters, then this is totally unambiguous, although a little hard to read based on the picture. I mean, I like this arrow thing a little bit better than these letters. All right, that's my little drawing lesson. Any thoughts about that? You will see when you're doing these on your own. If you may feel the temptation to draw it like this, don't do it. It's impossible to read that. it doesn't have enough information in this picture. How about one that does not have an Euler circuit? How about this? How about that? All right, let's give these guys names. Let's say A, B, C, D. Does this one have an Euler circuit or not? Actually, it doesn't, although it's not really easy to demonstrate. You know, if it does have an Euler circuit, you just draw it in there, and that's it, right? The harder situation is when it does not have an Euler circuit. This does not have an Euler circuit. I will just say, hard to say why. Of course, you can try to start drawing, like if I just try to start at A and I go down here like this, maybe come up to D, now go down to C, and now I'm kind of stuck because at this point, if you can follow where I went down that way, across the middle like this. Now next I could go back to A, but then I will have then I will get stuck if I try to go back to A. The only other place I'll have to go is back to the middle, and then I'll get stuck there. Or I could go back over to B, and I would get stuck there. So it looks like, at least if you start out this way, it's not going to work to finish an Euler circuit. But that doesn't mean that it's impossible. It just means that I made a boo-boo here. I did it wrong, but it doesn't mean it's totally impossible to do. It just means that I failed to do it. So hard to say why it's not possible. And this is really the thing that Euler did, which was useful, is a method by which you can prove for sure that there isn't an Euler circuit. To show that there is one is much easier. You just draw what it is. But to show that there isn't one is a lot more difficult. All right? I want to tell you about Euler's method. It's really Euler proved a theorem about Euler circuits. But the theorem uses some language that I want to get straight. So some language that you are going to see from Euler's theorem. Actually, there are many things in mathematics called Euler's theorem. This one, if I were talking to just like general mathematical people, I wouldn't just say Euler's theorem, because that means there are a lot of things that are called that. I would call this one Euler's theorem about Euler circuits. Is his famous theorem about Euler circuits. It doesn't really have a special name. But anyway, some language that we will see in Euler's theorem, and this is probably something that you've seen before in your mathematical career. The statement involves this phrase, if and only if. If and only if is a mathematical kind of catchphrase that you hear a lot in mathematical statements. It's not just trying to sound fancy. It actually has a very specific meaning to this phrase, if and only if. So I want to talk just a little bit about this particular phrase. Sometimes this is written like that. If with two F's means if and only if. I'm not sure who came up with the idea to write it as if with two F's, but if and only if is a important mathematical way of talking about things. So let me just tell you what that phrase means. So when I say something like A, if and only if, B, what this means that A and B are logically equivalent. All right, another way to say that is A and B mean exactly the same thing. Exactly the same thing. All right, A, if and only if B means the two things are logically equivalent to one another. All right, another way of saying this is, I will say, or it means both of these two things, if A, then B, and if B, then A, So when I say A, if and only if B, it means that, whenever A is true, B is also true, and also whenever B is true, A is also true. That's another way of saying just A and B, they mean the same thing logically. All right? Let's just do some very simple examples of using if and only if. So are these correct uses? How about if I say, I'm dressed today, if and only if I'm wearing pants? Is that a correct usage of the phrase if and only if? The question is, are these two things logically equivalent? Are they the same as each other or not? What do you think? I'm dressed today, if and only if I'm wearing pants. Is that the same? Like when I say I'm dressed today, does that just mean that I'm wearing pants? Are those the same thing? Or I would say no, not really. I suppose I could be wearing pants and not be fully dressed, I guess, or I could be fully dressed in a way which doesn't involve pants. Usually when I get dressed, it does involve pants, but I wear shorts sometimes. Does that count as pants? So anyway, I'm trying to say these are not logically equivalent to one another. So I'm going to put a big old X next to this one, all right? That is not an appropriate usage of the word if and only if. That's because the concept of dressed is not the same, is not logically the same. It's not equivalent to pants, right? I mean, there's some kind of relationship, I suppose, but they're not equivalent to one another. That's what if and only if is supposed to mean. How about this? I'm old enough to drink the alcohol if and only if I'm 35 years old. Is this a proper usage of if and only if? They're saying no. Yeah, I think it is not true that being old enough to drink, at least in these United States of America, is not equivalent to being 35 years old, right? It's equivalent to being, 21 years old or older. These are not equivalent to one another. It is true if you are 35 years old, then you are old enough to drink, but it's not true the other way around. If you are old enough to drink, it does not necessarily mean that you're 35 years old. All right, so this one also, not quite accurate. This is not a correct usage of the phrase if and only if. All right, how about this? I've seen the Statue of Liberty. If and only if I've been to New York City. In case you're just joining us, the Statue of Liberty is in New York City. Is this accurate to say I've seen the Statue of Liberty if and only if I've been to New York City? What do you think? I see some nodding. I see some shaking. Anyone feel strongly? An idea?
Well, I've been to New York City before, but I've never seen the Statue of Liberty.
All right. We got a witness here. She says she has been to New York City before, but she has not seen the Statue of Liberty. That's true. I mean, that's possible, right? I don't know if that's true. I assume that's true. We can all trust you, right? They're not the same, right? It's possible to go to New York City without seeing the Statue of Liberty. Yeah, I suppose it's also possible to see the Statue of Liberty without going to New York City, because it's pretty big, right? This is not an appropriate usage of the term if and only if. These are not the same thing, right? What is an appropriate usage of the term if and only if? It's really when you're just saying the same thing in two different ways, all right? That's what if and only if means. So a proper usage would be something like, x is an even number if and only if x is divisible by 2. That really is a proper usage of the phrase if and only if, all right? When you say if and only if, that's a very strong statement. It means these two things I'm saying are just like completely the same. There's no difference at all logically between the two of them, all right? X is an even number if and only if x is divisible by 2. Now this one, as I wrote it, it really looks very obvious that I'm just saying the same thing 2 times. There are other ways you can use if and only if, which are less obvious. Like I could say something like x is an even number if and only if x plus 1 is odd. This is also true, although this is less obvious, but it is true that being an even number is the same thing as saying the next number is odd. Although this is not, you might say this first one that I wrote is kind of like that's what even means. That's the definition of even. This is not the definition of even, but it's also true all the time that being an even number is the same as saying the next number up is odd. So that also is a proper usage of the term if and only if. All right? So I'm trying to say if and only if, when you say that, it's very strong. It means these two things are the same. They mean the same thing. All right? I think we're ready for Euler's theorem about Euler circuits. Any questions about this phrase, if and only if? I'm trying to impress you how strong the phrase if and only if is. All right, let's talk about Euler's theorem about Euler circuits. It says there is an equivalence. This has an if and only if. It says for any graph, actually, this is only true of connected graphs. Of course, if you think about it, if the graph as a whole is disconnected, there's no way you can do an Euler circuit. That would mean you use every edge and end up back where you started. But if it's disconnected, you could never get to the other edges on the other part of the graph. So it has to be connected. So for any connected graph, G, let's give it a name. The graph is called G. For any connected graph G has an Euler circuit. If and only if all vertices have degree, I was going to write degree 2, have even degree. All vertices have even degree. That's it. An Euler circuit is equivalent to saying that all the vertices have even degree. I should probably capitalize Euler. All right? This is Euler's theorem about Euler circuits. I don't know if this seems nice to you. This I would think of this as a really exceptionally nice theorem. I would say this is, would you mind me saying for a few moments? This is deep and powerful. Because I would say, because when I just look at a graph, it's not immediately obvious at all if there is or is not an Euler circuit. Like the bridges, the graph, all these graphs here, right? This bridges one or this one with the Mr. Plow streets one. When you just look at a graph, it's hard to say if there is or is not an Euler circuit, all right? But this part, so Euler's theorem is that having an Euler circuit is actually the same as this. All the vertices have even degrees. This is actually very easy to look at the graph and verify for yourself if all the vertices have even degree. That's why I would say this is deep and powerful. It says that Euler circuits are equivalent to even degrees. Deciding if there's an Euler circuit is a hard question, all right? This, I would say, is hard, but this is easy. If I look at a graph and ask, are all the degrees even or not? Remember, the degree is just how many edges touch each vertex. That's always very easy to tell if they're all even or not, all right? And Euler's theorem actually says that these two things are equivalent to one another. So it's taking a problem which on the surface seems to be a very hard problem, but boils it down to something which is actually very easy. This is a great theorem which turns something that's really hard, at least it seems to be, into something which, after all, turns out to be very easy. All right, so now that you know this fact about Euler circuits, you can immediately, when I show you a graph, you can immediately tell if there's an Euler circuit or not. So let's just look at a bunch of examples here. How about this graph? Is there an Euler circuit or not? The only thing that matters is if all the degrees are even. So I'm going to look at all the degrees of these vertices. I hope you remember how to decide what the degree is. The degree of each vertex is just how many edges are touching that vertex. So this one up top has degree 2 because it has 2 edges that are touching it. So I'll just draw that in. The one on the bottom is also a 2. The one on the left side is a 3 because there are 3 edges there. And the one on the right side is also a 3 because there are 3 edges touching the vertex over there. And in this graph, they're not all even, which means there is no Euler circuit. And that's all there is to it. To decide if there is an Euler circuit or not, all you got to do is look at all the degrees and see if they're all even, or if some of them are odd, then there is no Euler circuit. All right, how about Mr. Plow's neighborhood? This thing. Does it have an Euler circuit? Again, the question really boils down to what are the degrees, and are any of the degrees odd, right? If they're all even, then it does have an Euler circuit. If there are some odds, then it does not have an Euler circuit. What are the degrees here? Well, the one in the upper left corner is a 2, right? There are 2 edges there. How about this one right here? This one is a degree 3. That's because from this point I can see 3 different edges hitting it. There's this one, and this one, right? Here, here, and here. Be careful when you're looking at this, you might be tempted to count this sort of top line as just like one edge that goes through this vertex. That's not what it is, though. Every vertex has edges coming out of it. There's no such thing as an edge which goes straight through a vertex all at once. So this really counts as 3 separate vertices coming out of this one. All right? Actually, you don't even have to look at the rest of it. Just because there's an odd here, they are not all even, and so there can be no Euler circuit in this graph. So I will say again, not all even. Actually, if you look at the rest, there's more 3s. There's a 2. These ones in the middle are 4s. But anyway, they're not all even. That's all I care about. So no Euler circuit. All right. How about something like, anybody got questions about this? I hope that you feel like this is very easy. If I just show you a graph, you can immediately tell me if there's an Euler circuit or not. Can you just try? I'm going to draw 2 more. See if you can tell in each case, does it have an Euler circuit or not? There's one. Here's another one. I'll give you 3. Remember that guy? All right, for each one, tell me, does it have an Euler circuit or not? If your answer is yes, it does, then try and draw one in. If your answer is no, it doesn't, then tell me why it doesn't. And your answer always involves because there's some odd vertices in there. See what you think. I'll give you a few moments. So your job is either draw an Euler circuit or say it doesn't exist. I'll give you a few moments. you should always start by thinking about the degrees. Okay. All right. All right. Can I make a suggestion? This would be an example that I can't tell where you started. And so, for instance, where do you go next? You should draw your curve all in one continuous line, which doesn't actually go through like this. Yes. Yeah. I don't know why I didn't draw it. It doesn't really make sense to have edges that go to nowhere. Yeah. Okay. I suggest All right, you want to talk about these? I see a lot of good answers and some some drawings which are not possible to understand. So I will refresh your memory of my artistic tips. Anyway, the first one, you should first look at the degrees everywhere. So this is a 2. Down here, this is a 4. That's a 4, and that's also a 4, and that's a 2. They are all even, which means, yes, there is an Euler circuit in this graph, and I'm going to try to draw it because that's what I said you should do. Either draw it in or say that it cannot exist. Now, there are many different possible Euler circuits here, but I will draw one, say, starting at the top vertex. And I will remind you, you have got to draw your path so that I can tell where it goes from one step to the next. All right? I saw a lot of people sort of doing like this, like that, and then that, and then that, and then that. This is not good enough because, for instance, I go up here and then back down there, over there, and then up there. This is not good enough because now when I look at it, I say it comes down here, and then which way does it go? It could go that way or down that way, but it's not obvious. If you're going to draw arrows like this, you have to connect them up one to the next. So a proper way of drawing this would be something like that. That goes here, and then from here it goes up to there. From here it goes down there. From here it goes over there. From here it goes up there. All right, I like that much better. I'm not just trying to be picky about the drawings. It actually has to connect up in order for it to make any sense to me when I'm reading it later on. All right? I hope you drew something like this where I can actually tell what it means. Okay, what about this one over here? Again, you should begin by checking the degrees and seeing if they're all even or if there are some odds. So here is a degree 2, a 2. What about this one here? That's a 4. I saw some fingers. This one up here, I count 1, 2, 3, 4. So this is also a 4, and the one down here is also a 4. So this one, I believe, does have an Euler circuit because they're all evens, and then I'm going to draw it in. Now we're going to talk next time about exactly how do you decide where to go when you're drawing the edges in, but for now, these ones are small enough that you can just kind of make it up, and it should work pretty well. I'll go around, maybe I'll come around the outside here. I'll go up and then back down again and then back up again and across back to where I started. I think that will do it. There are many other ways you could have done this, but that's one way at least. If you want to be totally unambiguous, you could give names to all the vertices and then write out your answer in terms of the letters. That would be completely unambiguous. Although it's fine with me. If you would rather just draw your lines like this, that's fine with me. All right, and how about the last one? Again, look at the degrees. What are the degrees in the third one there? I see the signal. They're all 3s, right? East Coast. Is that what this means? This way. They're all 3s. 3, 3, 3, 3. So no Euler circuit, right? In order for them to have an Euler circuit, they have to be all evens. And these are all odds, actually. So this one has no Euler circuit. All right. Any thoughts about those? I hope that everybody feels okay about the Euler circuits. It's actually very easy to tell if there is or is not an Euler circuit. Can we just look at the OG, Euler circuits problem? The Bridges graph, right? This is how Euler eventually figured it out. This was the original graph from the Bridges problem. Does it have an Euler circuit or not? You look at the degrees. I see 3, 3, 3. The one on the left is 5, right? They are not all even, and so immediately you can say there is no Euler circuit. This particular problem is something that real smart people spent years trying to think of this problem, and it takes you less than 10 seconds to figure it out if you know the trick. This is why this is like a truly awesome trick for this problem, because there is no real simple solution unless you know the trick, in which case everything is totally simple, right? It's a great theorem, Euler's theorem about the Euler circuits. I would like in the remaining 9 minutes to try to explain why is it true. So, why is degree even equivalent to Euler circuits? Does it make any sense that all the degrees have to be even in order to have an Euler circuit? It does make some kind of sense. So I don't, really, if we were going to be real hardcore about this, we would go through like a detailed proof of this. I don't want to get into that, but I would like to give you some idea of what the relationship is. Why should you believe that there is a relationship between all even degrees and Euler circuits? So what I would like to think of is, how about imagine that there is an Euler circuit. And let's just try to think about what the graph looks like at some particular vertex. So this is, and I would like to zoom in at some vertex. All right. Now, this vertex has a bunch of edges coming out of it, which go into the rest of the graph, but I'm not trying to draw the whole graph here. I'm just drawing one vertex, and it has a bunch of edges coming out of it. All right. Now, if there is an Euler circuit, what does it look like when I draw in the red line? We can't say for sure what it looks like, but if there is an Euler circuit, it means at some point that red line has to maybe come in here and come out this way, right? The Euler circuit has to use all the edges, and so maybe it does some other stuff over here and eventually comes back along this one, maybe it goes out along that one again, and then does some other stuff, and then maybe it comes in along this one and comes out along this one again, right? This is what the Euler circuit looks like in our graph. It has to arrive at this particular vertex every so often, right? And actually cover all of the edges that come into this vertex. Can anybody suggest, anybody have a feeling, like what does this have to do with the degree being even? Like on this picture, the degree is 6. And you can see this Euler circuit, it comes in here and then goes back out. It comes in here, goes back out here, comes in here, goes back out here. Does it have anything to do with the fact that 6 is even actually makes this possible? You get an idea?
The fact that the circuit has to enter and exit, that's a factor of 2, so it has to come out once and then leave once every time.
Yeah, right. This is all about arriving and leaving, or coming and going, right? It has to come in and then go out every time that it arrives at this point, right? They always want to come, but they never want to leave, as the lady says. In an Euler circuit, it has to come in and then leave every time, all right? Because it doesn't get stuck here. So it has certain edges on which it arrives and certain other edges on which it leaves. So I'm going to say it in this way. Each vertex must have some, I will call them arriving edges, and the same number of leaving edges. And this is why there has to be an even number, because it has, it's like half of the ones are sort of arrival edges, and the other half are the leaval edges. And there's no extra one left over, because that would mean either the Euler circuit missed an edge, or maybe it came in but never left, which is not allowed. All right, so this means, so the degree must be even. All right, this is the basic idea. This is not a real proof, but this is the basic idea why you should believe there is some relationship between even degrees and Euler circuits. There really is. All right, and I think that will do it for us. We got a few more minutes, but if anyone wants to talk about the homework, I'm good for it. Otherwise, I'll see you on Friday.